Algebra 1, lesson 9.7. So what's going on with this lesson is this just a brief piggyback onto lesson 9.6. Because what's going on with lesson 9.6 is exponential functions, and we even use the terms exponential growth and exponential decay. And the reason why those terms were used is that a lot of stuff grows or decays at exponential rates. So, like for example, you put money in a bank account, and the bank account pays you compound interest. Now, what compound interest is it's interest where you earn interest on the initial amount that you deposited, as well as any interest that you have earned since you deposited the money. Okay, so your interest pays interest on the original amount and any other interest that you've earned. And compound interest, when you graph what's going on and when you analyze what's going on, it is an exponential growth. So the longer that it sits there, it grows faster and faster and faster. Why? Because the longer it's been in there, the more interest that it has earned. And so then when you earn interest on that extra amount of interest, it can end up, growing a lot. So, like for example, if you got a job when you were, I think, 18 years old, and you earned $1,000, and you invested that $1,000 in a retirement account that earned like what the stock market overall averages over time, which is usually right about 8%, historically is what is averaged. Then that $1,000 that was sitting there from the time that you were 18 years old and you did nothing to it other than just let it keep earning interest. When you were ready to retire, let's just say 70 years old, so you usually think of like 65 years old as retirement age, but as health, as what am I trying to say? As health standards and healthcare improves, people are living a lot longer, and most likely by the time you're retiring, it might be something more like 70 years old is a more common retirement age. Anyway, $1,000, put it in a retirement account earning 8% interest when you are 18, 16, 17, 18, right around in there. By the time you're ready to retire, it would be around $250,000 of doing nothing but just sitting there. Then let's just say you're able to add $10 per month to it over the course of those years. Then you'd be looking at more like $500,000, $600,000 that would be there just by that initial amount when you're fairly young, and that would be something like a Roth IRA is what would be good. But that's a different discussion. But anyway, radioactive substances decay at an exponential decay thing. Populations oftentimes grow at exponential rates, at least for a while, and then it kind of levels off because there are space limitations, there are resource limitations that make it so oftentimes things grow exponentially for a little bit and then it levels off. So, all that to say, lesson 9.7 is a little piggyback onto lesson 9.6. This is 9.7. I'm going to use black because that's what I've been using for these notes. This is 9.7, and this is called growth and decay. All right. So what we have is we have a couple specific formulas that we're going to use that model exponential growth and exponential decay. What we have here, this is our exponential growth equation. Exponential growth. We can write an equation like this. Y equals A times 1 plus R to the power of t, where y is final quantity. I'm going to use QTY to abbreviate quantity. Hopefully you're okay with that. A is initial quantity. R is growth rate as a decimal. In other words, if something is growing at a 10% rate, you do 0.1. If something is growing at a 25% rate, it'd be 0.25. 0.25. If it's growing at a 5% rate, it'd be 0.05. Okay, so R is a decimal. And then T is number, well, yeah, of time, T is for time here, time intervals. And I'm just going to leave it at that because it depends on what your rate is based on. So if R is an annual rate, then T would be number of years. Okay. If R is a daily rate, then T needs to be number of days that you're dealing with. Okay. So let's do an example. Let's do an example. Let's say, let's see, what do I want to deal with? I'll go with the population of butterflies. A population of butterflies is growing exponentially at a rate of, I'm going to go with 14%, at a rate of 14% per month. If the current population is 850, what will be the population in 1 year? Okay, so let's see what we know. Do we know what A is? The initial quantity. Yeah, A is 850. Okay. Do we know what R is? The growth rate. Well, the growth rate is 14%, so I'm going to represent that as 0.14. Do we know what T is? And here's where you need to be careful. To make T, use the same units as R. So R is 14% per month. So T needs to be the number of months. So if I want to know what the population will be in 1 year, I need to express 1 year as how many months that is. So T is 12 months. Okay, now I can plug in what I know. My formula is y equals a times 1 plus r to the t. That 1 plus r makes it so if r is anything greater than 0, if r is a positive value, then your base, this is drawing on lesson 6 stuff, then your base here is a value greater than 1, which gives you growth. And we'll see this in our next example. But if r is a negative number, use negative rates for decay. If r is a negative number, then 1 minus some decay rate will give you a base that is between 0 and 1, because you can't have a rate of decay greater than 100% decay, because 100% decay means it's all gone. Yeah, then you get a base between 0 and 1, which gives you exponential decay. Anyway, all right. So let's plug in what we know. What do we know here? We know that we have 850 times 1 plus 0.14, which gives me 1.14 to the 12th power. And I use my calculator, and I carefully do. Now, depending on the calculator and how sure you are with how it calculates things, I usually like to do this part first, 1.14 to the 12th power, and then I take whatever that is and I multiply it by 850. In this case, 850. So that's how I'm going to do it, because I'm using a calculator on my phone, and I don't know as well how it works. So I'm going to do 1.14 to the power of 12, and that is about 4.818, so almost 5. So my population here is going to be almost 5 times as big. So now I need to multiply that by 850. Oops, hold on a second. I didn't hit equal yet, and so I did the times 850 as part of the exponent. Backspace. Okay, enter, or equals. Now I can do times 850, and that gives me approximately 4,095. Now it's technically 4,095.2. But here's the thing. What is 2/10 of a butterfly? Given the context, decimals don't really make sense. So I'm going to leave this as 4,095, which you could be like, oh, okay, so it's regular round. It's like, well, it's not quite regularly rounding because what if I had 0.9? I would argue that because this is growth, if we have 4,095.9 butterflies, we haven't quite gotten that next butterfly yet as far as the numbers are concerned. So I would still keep this as 4,095. So that's my answer, 4,095 butterflies. Okay? So that's my answer. Now your homework has like, part A, write the equation for this situation. That would be like this. Part B, solve the equation. That would be my 495. Part C, write the answer in a sentence. So it'd be something like, there will be 4,095 butterflies in 1 year. That would be writing it as a sentence. Okay? Hopefully that makes sense. All right, one quick one with decay. So let's just say a substance, I'll just make this really generic, a substance decays at a rate of 41%. Oh, per what? 41% per year. If there was initially, let's just say 5.0 grams of it, how much will there be in 7 years? Okay. Well, let's list what we know. And we'll list our formula. Maybe I'll list our formula first this time. We have y equals a times 1 plus r to the t. All right, a is the initial quantity. That's 5.0 grams. R is the rate. Now remember, if it's decay, it's a negative rate. So R here is negative 0.41. 41% decay would translate to negative 0.41. And then T, well, let's see, my rate is in terms of years, and I'm being asked how many in 7 years, so T is 7. I don't need to adjust my units of T at all. So plug in what I know. I have 5 times 1 minus 0.41 to the 7th. Well, that's the same thing as 5 times 1 minus 0.41 is what? 0.59 to the 7th. Okay? So I'm going to do my 0.59 to the 7th, 0.59 to the 7th, and then times 5, and I get approximately 0.12 grams. That's how much will be left. So that'd be like my part B answer. This would be my part A answer. This is my equation for this situation. So part A would be that, part B would be that, and then part C would be to write it out in a sentence. Something like, there will be 0.12 grams of the substance after 7 years. Something like that. All right. Then one more equation is specific to money. This is our compound interest equation. Compound interest. compound interest. It's the exact same formula that we've been dealing with, just slightly represented in a different way to make it specific to compound interest. So we have here is we have A equals P times 1 plus R over N to the NT. Okay, so here's what's going on. A is our final amount. Final amount. P is initial principal. R is annual rate. N is number of times compounded per year. If you're dealing with money, it's almost always compounded monthly. Okay, so what that means is each month the bank looks at how much money you have in your account and then they give you interest. The next month, give you interest. The next month, give you interest. Okay, and then T is number of years. Number of years. Here we don't have to adjust the T. Well, our R is years and our T is years. And then the N times T gives you the total number of time periods. The R over N puts the rate in terms of, if it's like compounded monthly, the R divided by N gives you the monthly interest rate. And the N times T gives you the number of months. If it's interest that is compounded daily, which, it raises, well, let's just say weekly, 52 weeks in a year. The R over N gives you the weekly interest rate, and then the N times T gives you the total number of weeks. Okay, but let's go with the example that we gave before. So let's just say that we have an initial investment of $1,000. Let's say we have an annual interest rate of 8%. And let's say you deposit at 18 years old. At 18 years old, and you want to see how much you have at 70 years old. So that would be what, 52 years? Okay. And we'll say it's compounded monthly. All right, let's see what we get. So plugging into our formula, we have A equals P. P here is 1,000. Times 1 plus R, but as a decimal, so 0.08 over N is compounded monthly, so it's over 12, to the power of 12 times 52. Okay, let's start to break this down and see what we get. So I have 1,000 times. Let's look at what 0.08 divided by 12 is, just to break this down in bite-sized chunks. 0.08 divided by 12 is 0.06 repeating. 0.06. I'm going to put the bar over that. That means repeating. So 0.0666666666. It goes on forever, but I'm just going to do a few sixes and then round it at the last one up to a 7. And then 12 times 52 is 624. 624. Okay? So that's the same thing as 1,000 times 1.066667. I'll do that to the 624th power. Okay, so I'm going to do 1.066667 to the power of 624. And that gives me a very large number. That gives me too big of a number. What did I do wrong? Compounded monthly, annual rate, 8 point. Oh, here's my mistake. This is why I don't mind doing these on the fly and making mistakes. 0.08 divided by 12 would not give me 0.06. 0.06 is way too close. I'm missing a 0. That's what it is. I'm missing a 0. This is why you don't just blindly punch stuff in your calculator without thinking about what you're doing. So I need to insert, so this should be 0.006. So what I'm going to do, I'm going to erase that decimal point, erase that plus sign, and this is oops, sorry. That was, I meant to be that as a plus. 1 plus 0.006. So that's going to change what's in here. It's going to change what's in here to be 1.0066667. So I needed one more 0 in there. Okay, now I can do 1.0066667 to the power of 624. And now what I get is, so that gives me 1,000 times 63.194. 63.194. And what does that give me? 1,000 times 63.194. So that times, nope, I gotta hit enter again. Delete, 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 delete. Times 1,000. And that gives me 63,194.38, which is not the what it was thinking before, like 250,000. I wonder if that's if you deposit at 16 years old. So if I added 2 more years here, so rather than 50, so oh no wait, 18, yeah, 18 plus 52 is going to give us 70 years old. So what if I make that a 54 instead? I'm just curious. 1.00666667 to the power of, instead of 12 times 52, we do 12 times 24. Sorry, 12 times 54. 12 times 54 times 1,000. And that bumps it up to 74,000. So I need to double check what that initial deposit amount is. It would give you about $250,000. But still, that is not bad, even with what we have going on here. To start out with a $1,000 investment and let it sit and do nothing other than, gain that 8% interest, which is a pretty good rate of return. That assumes that the stock market keeps doing what it has historically done over the long haul. For that $1,000 to sit there and, due to the power of compound interest, end up becoming over $60,000. Yeah, that'd be cool. All right, hopefully that example helps with compound interest, and I think you have 4 word problems to do for this lesson, and that's it. So, as always, let me know if you have questions. Thanks. Bye.